Hello everybody, we're going to finish module 14 today. So we're going to get started on page 474 plus in your textbook. Using rate equations to find the instantaneous rate. So instantaneous means in that precise moment in time. We have a problem. Because as soon as the reaction starts, the concentration of the reactants decreases. It's being transformed into product. So the amount of reactants is getting smaller and smaller. Here we have a graph in which we can see that the rate is also decreasing in time because the concentrations of the reactants is decreasing. It slows down the reaction to have reactants available to react. The rate calculated using the rate equation that we saw last week is an instantaneous rate. So it's the rate at that precise moment when we have those concentrations. It tells us the rate for the reaction at a point in time with the concentrations of the reactants we have for that point in time. Figure 14.1 on page 475. How the rate of a reaction changes over time. Decreases. Given a general reaction, A plus B giving you A and B, the rate of that reaction decreases as the concentration of A and B decrease. The rate is the largest when the reaction starts, because that's when you have the most reactant. But look how steep this is. After a short period of time, it slows down to a crawl. It never reaches zero, but it goes very, very slowly. Figure 14.2, how the concentration of a reactant changes with time. We're on page 476. The concentration never reaches zero. There's always a tiny bit of reactant left over. And as we're going to see in the next module, there's always some of the reactions go on both ways. So reactants become products and some of the products go back to becoming reactants. And you'll see that in the next module. So there's always a tiny bit of reactant left, never reaches zero, but it kind of flattens out very close to zero. So chemical reactions never actually finish. It's kind of strange to think about it that way, but it's true. They get slower and slower, but there's always some reactant left. One way to calculate the rate of a reaction at a moment in time is by using the slope. But we're not going to use that mathematically. We're not going to do that. So figure 14.3, how the rate constant depends on temperature. If you remember, the rate equals a rate constant, the concentration of reactant A, exponent X, concentration of reactant B, exponent Y. And remember that the order of these for each one of the reactants is calculated by experimentation. Okay, it's also calculated by experimentation. Temperature does not appear here, but temperature affects K. And here is how it affects it. The rate constant increases with temperature. As the temperature increases, that K is increasing. It's multiplying here. So as temperature increases, K increases, and the rate also increases, which we know it to be true. You're giving it energy, more collisions, the faster it can go with that reaction. We are going to use a rule of thumb from now on. Well, actually, let's put it this way. If they're telling you that the temperature is changing, we are going to use a rule a rule of thumb to calculate how the rate changes because there is a change in temperature. And here is the rule of thumb that you're going to be using. K, the constant, will double for every 10 degrees Celsius that increases in temperature. So you count how many increases by 10 you have. Each one is a double for K. The same is true in reverse. If the temperature decreases by 10 degrees, you're going to divide by 2. For every 10 degrees, you're going to divide by 2. And we're going to see a problem in which you're going to apply this information. Here it is, page 478. Example 14.5. Says a chemist performs the following reaction at a temperature of 25 degrees Celsius, and they give you the reaction. In an earlier example, we determined the rate equation to be, here it is, the rate constant for a temperature of 25 degrees. They give you the rate. What will the instantaneous rate of the reaction be at 25 degrees if he runs a reaction with both reactants at a concentration of 15 molarity, 0.15 molarity? What will the rate be if he runs a reaction at 45 degrees Celsius instead? Now we're going to do an extra practice problems. So there are different steps here, different questions. Let's look at it just one at a time. Let's go to the board and let's see here. So what do we have? The rate equation looks like this. This was given to us. Okay. They also said that at 25 degrees Celsius, the rate constant, the rate constant, I need to read this right. The rate constant here, okay, equals 0.15, 1 divided by molarity 2 times second here. What will the instantaneous rate of the reaction will be at 25 degrees if the concentrations for each, so the concentration for NO equals 0.15 molarity, and also the concentration of the second one, Cl2, also is 0.15 molarity. For this section, the only thing we need to do is plug everything in. So the rate is the constant at that temperature, 0.15. Remember that each one of those constants have different units, so be careful with those units. Multiplying the concentration of NO to the second power, so 0.15 molarity to the 2, and the concentration of chloride to the 1 power, to the first power, so 0.15 molarity. Okay, so let's see. This, all of it, in your calculator, comes out to 0.00051 molarity per second. That's the first question. This is the first answer that we need to give. The second section here says, now the temperature has increased. Let me do it differently. We're going from 25 degrees Celsius to 45 degrees Celsius. Remember that when there is an increase in temperature, we are using a rule of thumb that says that every 10 degrees, so 25 to 35, and then to 45, okay? Every time the constant is being multiplied by 2. That's what we learn. I mean the rate gets multiplied by 2. So the rate multiplied by 2, and here when we go from here to here, the rate will be multiplied, this rate 2 multiplied by 2 again. Okay, so we're multiplying by 2 every single time. What was the rate here? So at 45 degrees Celsius, start with a rate. Our original rate that we just found is 0.00, another 0, 51, molarity divided by second, and we're multiplying it by 2 for the first jump, and then multiply it again by 2 for the second jump. So if you do that, you get that the new rate, using our rule of thumb, is 0.0020 molarity per second. Okay, so just break down what's going on with the temperature, and remember that the rate doubles as you increase by 10 degrees Celsius. Every 10 degrees, multiply by 2. If it decreases by 10, divide by 2. So this one is done. Then I want you to go to page 582 and try extra practice problem number 5. I'll give you the answer, and of course, if you have it, you got it, move on. If not, check to see how it's done. Okay, let me read it. A chemist runs a chemical reaction at 25 degrees and decides that it proceeds far too slowly. As a result, he decides that the reaction rate must be increased by a factor of 8. At what temperature should the chemist run the reaction to achieve this goal? Well, the answer for this is temperature needs to be 55 degrees Celsius. You got this, you did it right. You can try again or not. So what is increasing by 8? Remember that we're multiplying by 2s. Every 10 degrees is a group of 2. So what is x to make an 8? What exponent will make that 2, because we multiply by 2 every time, will make 8? Well, x equals 3. Okay? So that means that you increase the temperature 3 times by 10. Everybody sees that? You started with 25 degrees, and then you jump first time, it's the first time we did, to what? To 35 degrees Celsius. Second time, it went to 45 degrees Celsius, and here's the third jump. It went to 55 degrees Celsius. So that's where our answer came. If you wanted to increase by a factor of 8, how many jumps did you have to do? You had to do 3. 3, because every 10 degrees you multiply by 2. So that's done. Okay, let's go to instruction and see what's going on next. More about catalysts. I promised you that we were going to see it in more detail. So page 480 plus in your textbook. You will be performing an experiment this week, experiment 14.2, in which you're going to be looking at the effects of a catalyst on the decomposition of hydrogen peroxide. You need to remember that catalysts speed up the reaction rate without getting used up in the chemical reaction. You put it in, it helps the reaction to go faster, but at the end you have the same amount of catalyst left. And they do that by decreasing the activation energy of the reaction. This is review, figure 14.3. The reactants right here, products right here, means it's exothermic. Great. Activation energy, how much energy you need to get started, pretty high. You put a catalyst, it reduces the amount of energy needed, speeding up the reaction. That's what it does, and it does not get used up. There are two kinds of catalysts: homogeneous catalysts and heterogeneous catalysts. Page 481. Homo means the same, hetero means different. Homogeneous means that the catalyst is in the same phase as the reactants. In this case, they are all liquids. Heterogeneous means that the catalyst is in a different phase from the reactants. So you have a liquid and a solid, for example. And here's a definition, and you need to know that. So homogeneous catalyst is in the same phase as the substances reacting. Heterogeneous, on the other hand, is a catalyst in a different phase. And the book gives you examples. Page 482, they give you an example of a heterogeneous catalyst. The catalytic converter in your car is an example of a heterogeneous catalyst. These are metal, and this catalyst, your catalytic converter, helps carbon monoxide that's produced in your car to become, which is extremely poisonous, to combine with oxygen in the air to become carbon dioxide, which is less poisonous. It's still not good, but it's less poisonous. So how does it do it? Well, carbon dioxide and oxygen both are attracted to the metal, which is platinum. Okay, it's a platinum catalyst surface of your converter, of the catalytic converter in your car. Because both of them are attracted to that metal, they attach themselves to the metal. And that puts them in close proximity. Once they are in close proximity, they can do their reaction and become carbon dioxide. Then they disappear and the metal is left there behind to do it again and again and again. So you're going to have to be able to explain how a catalytic converter works back to me. Here's an example of a homogeneous catalyst, so the same phase, page 483. You have the reactants. The catalyst is put in to lower the activation energy of the reaction. They both attach themselves to the catalyst. This is called the intermediate product. And then, because they're both in proximity to one another, now they react with one another and the catalyst comes out again. Back the same. Nothing happened to this catalyst. It has not reacted. So catalysts use steps, breaking the reaction into easier... Oops, I touched the mouse again. I'm sorry about that. So, let me read this again. They use steps, breaking the reaction into easier chemical reactions. So, combining and creating this intermediate product lowers the activation energy. This, the fact that there are steps now, it's not directly those two combine to create the product. There's a middle step. It's called a reaction mechanism. So you need to know the definition of a reaction mechanism. It's a series of chemical equations that tells you the step-by-step process by which a chemical reaction occurs. Here's another example. You're going to find this example on page 483 in your textbook. Although this reaction is spontaneous, thermodynamically speaking, the criteria thermodynamically is correct, is spontaneous, is very, very slow. We can speed it up by using a homogeneous catalyst. How? Well, this is your catalyst. And you know it's your catalyst because it's added at the beginning. It's going to appear as one of the reactants. And it will appear again as a product, unchanged. Same amount, no changes. That's your catalyst. What happened here? In step 1, your catalyst reacted with the oxygen, which is one of the reactants, and created an intermediate product. The intermediate product then reacted with the second reactant in the equation, creating the product we're looking for. And of course, leftover catalyst that is not being used up, because that's the definition of a catalyst. It doesn't get used up. It just lowers the activation energy of the reaction to speed it up by creating an intermediate product that is easier to react with the second reactant. This ends the second half of module 14. We're getting closer and closer to being done this year. Read your textbook, add to your notes. Work examples, again, if you need to. Work on your own as you encounter them. Correct as you go. Study for your quiz. Do the lab. We'll talk about it during our Zoom meeting. Review questions, self-correct, practice problems, self-correct using the answer key first. And I'll see you on Friday. Bye-bye.